All right, should be recording there. Okay, good. So good afternoon, everyone. So before we start, just some house announcements. I hope all of you will listen to Shiva's voice note. But just in case you didn't get a chance to, basically he said we understand a lot of people might not get bonuses or might be laid off or a bunch of other things in the pandemic, and we're trying to help by cutting the cost of the class. So I think it was 4,300 before, and he brought it down to 3,300 now. So for anyone who paid the full amount, just check him, just message him and see what he could arrange. But for everyone else, yeah, it's 3,300 now. So you can listen to the voice notes for the other stuff he said. But that was the gist of it. So yeah, we saving a lot of money on the infrastructure cost, so we passing that along to you because it's only fair. And that was it. Yeah, I think that was the gist of what he said in the voice notes. Right, so back to the CCNA class now. I hope you all following along in the classes and on the videos on YouTube if you need to, and the textbooks and CBT nuggets as well, of course. Let me know if anybody lost anywhere. If there's any topic that you're not comfortable with, if any lab giving you trouble, if you're just feeling lost on the whole. I will very well send a 20-minute voice note and explain the whole syllabus, just summarize it and catch up to where we are. I want to make sure just everybody on the same page, more or less, and at the very least, you're up to here and you know what we're doing. More or less, you don't need to understand everything to a T and ready to take the exam tomorrow. But if you at least have a gist of what we do so far, and when I say routing and when I say prefixes and network masks and all of those things, right. So okay, so the wildcard masks, I'll go into that in OSPF. But that's at least that's a future topic. So don't worry about that too much. The past topics are mostly concerned about. Yeah. If you want, I'll hit you a message or a voice note or a call on the wildcard masks. But when we go into OSPF and static routing, you'll see the wildcard masks a bit more. I think wildcard masks mostly used in OSPF. So you'll see some examples of them as we go along. But yeah, anything else past especially, anything in these sections, anything in this section, hit my message personally and we'll have a call or we'll go through it. Yeah, wildcard masks, we should be able to cover that somewhere in OSPF. Right. So, hope it's not. Okay, good. Right. So today, well, let me start from last class first. So, all right. Go up a little bit here. We'll split in the class here. Okay. So, we in the middle of section 3 here, right? So just as a reference, I always like to use this. So we have 6 main sections. We in the meatier section. So the nice 25% there. I would say before this version of the CCNA, this was my favorite section because it contained the most material. So as I mentioned before, if you could go in an interview, in any entry level networking or sysadmin job, and you could talk about these things. You could talk about prefixes and network masks and administrative distances, longest match lookup, all these kinds of concepts, even if you can't implement it. If you could at least discuss it in an interview, you'll impress a lot of people with your technical knowledge, which is why I used to like this section a lot. And I still like this section a lot. But honestly, this section is my new favorite section. So you'll see when I reach here, you'll see why. A lot of people don't know anything about this section because this is the very first iteration of the CCNA where they introduced it. And a lot of people, I know CCIEs who are not comfortable with this stuff yet because in the past, CCNA was always 1, 2, 3, 4, and a little bit of 5, and that was it. 6 is completely new. So that's why I like this. It's a brand new plate, and if you could master this, you'll have real work anywhere in the world. A lot of remote jobs and a lot of things. Ask about section 6. So when we reach there, you'll see all the fun stuff. But for now, you need to understand the basic stuff before you can automate it. You can't automate what you don't understand. That's a general rule for anything. So for today, we will be going through, so we went through 3.1 and 3.2 in the last class. So I hope when I mention next hops and administrative distances and longest match lookup and routing protocol metrics, so metrics, you will at least have an idea about what I'm talking about. We'll do a little recap of them, and then today we'll start off with static routing. So this is where we're gonna actually get into the routers and try to configure them. So, tell the router, okay, if you want to reach this network, go here. And we're gonna see, well, we'll introduce both concepts. You'll see we'll do manual pointing or manual configuration, which is static routing, basically telling the router if you want to go to network A, go to here. If you want to go to network B, go to here. And every network you have in your big network, you need to tell your router that. And that's what static routing is. So we'll go through those concepts and those configs, and then we'll start off today. So today I'm actually going to split this topic because OSPF is a fairly large topic. And I didn't want to cover both static and OSPF in the same class. So that's what I was doing here, and splitting it up a little more. So we'll go through all of static routing today and around half of OSPF. And then Tuesday, we'll go through the next half of OSPF, and then 3.5, and we'll start off 4.1. So yeah, you'll see in the rest of sections, they all like this. So instead of breaking it down like this, A, B, C, D, they kind of just stuffed a whole set of topics, 0.1, 0.2, 0.3, 0.4, and they make them all, it's 10%. So I wouldn't spend like a whole class on 4.2 here, because it's really a small concept and a small bit of configurations, which is why they didn't split it up too much. So we'll go through like half of OSPF and this in the next class, and from then on we'll move in fairly quickly to finish out the class, but is 10%. So I'm making sure I'm spending more time on the heavy stuff, and OSPF I would say is probably the heaviest topic I did in my CCNA class. So I want to make sure I'll cover that well. So let's begin. I didn't pick anything. No, went over topics, and we're recording. Good. And pointer. Right. Let me know if you all not seeing the pointer or anything. It's still loading a little bit, but we should be good. Right. So first, a brief recap of the last class. So last class, we examined the concept of a routing table, illustrating how a router builds its knowledge of various networks or routes from a number of sources and directs or forwards packets using this information. So the routing table, just like the switching table, is just the knowledge that a router has. Oh, you're not seeing the screen? Okay, 1 second. Anybody else not seeing the screen? Oh, everybody not seeing the screen? Stop sharing. Okay. Okay, let me know if or when you've seen it. It should be shared. Yes, I'm gonna stop sharing it and reshare it. Share screen. Okay, let me know. You should be seeing the screen there. Seen it? Nice. Okay, good. Let me know if anybody else not seeing the screen or anything. Okay, so yeah, last class we covered the routing table, and the routing table is, well, we'll see a screenshot a few slides ahead, but the routing table is the knowledge that a router has. So every network that a router knows how to reach or how to route to, this routing table captures that information, and it displays it in a nice, a nice column table format. And it's the same concept as a switching table. The difference is that we have a wide number of sources that we could use to populate this table. And then, of course, the whole purpose of populating this table is to direct or forward packets using this information. So the router is going to use the information in that table and send packets along, however many interfaces it has using that information. So we perform this examination by examining examples of routing tables and moving left to right, examining all of the various parts of the table. So the routing table it seemed very complicated when we started off, but I hope by now you could watch a routing table and you could understand the different components of it and not just see, some madness. Right. So this is what the routing table looks like, of course. So it's just text, but we could kind of see the tabular format here. So we know at the top we have these codes. So these codes and these letters here tell us where the routing table sources its information from. So the local, the connected, the static, RIP, BGP, EIGRP, OSPF. OSPF should be somewhere there. And you have a bunch of different codes for a bunch of different subcategories within those big categories. But in a nutshell, these codes just tell us, we learned this route from this source. So we see this route here, C, and it'll tell it in words too, is directly connected. So C is connected, it's a connected route. We learned it because it is directly connected to us. D is dual, so EIGRP is not in the syllabus anymore. So I won't go into the details about it. But D is used for EIGRP, even though it doesn't have a D in there, because it runs the dual algorithm. So if we learn routes from that algorithm, we put a D next to them. S is for static, so we'll go through static routes today. R is for RIP, and you'll see a O for OSPF if you're on an OSPF. See O, OSPF, right? And then these are the networks, these are the subnet masks, and then some of them might be subnetted, some of them may just be the giant networks, because Cisco will always try to make a supernet out of it. And then we have the next hops. So you see the next hop, gigabit 01. So they took out the EIGRP because honestly, a lot of people moving away from EIGRP. So the very first thing to learn about EIGRP versus OSPF is that EIGRP is Cisco specific. So as in Cisco engineers developed EIGRP, and they wrote out the standard and they kept it closed source for a number of years. So HP and Huawei and Juniper and these other guys, they couldn't implement EIGRP at all. And what eventually happened was a lot of people couldn't afford Cisco devices now. So even though Cisco is still the big boss, people they can't afford full-on Cisco network stuff, not through the whole network. So what happened was you would have, let me say, you have 3 Cisco routers and 2 Juniper routers. And between them, you could choose to either run EIGRP or OSPF. And then you realize Juniper can't run EIGRP at all because they don't have the code for it, because Cisco keeps it closed sourced. So eventually they realized people were running OSPF because of that, and they opened up EIGRP a few years ago. They open sourced it. Well, not really open source. They kind of opened it up so that other people could implement it. But by then, most vendors already went to OSPF, and OSPF is a pretty robust protocol. There are a few things in EIGRP that a lot of engineers like. It has better, better load balancing. So EIGRP could detect when your link's loaded versus not loaded. When they're running at 90% of capacity and all those things. So it is better in some ways, but largely OSPF kind of won there because it is open source and a lot of vendors could use it. And in a lot of networks, I'll tell you, at least in Trinidad, a lot of networks are mixed. People run, Juniper next to Cisco, next to Huawei, next to MikroTik, or next to HP networks. They do a lot of stuff. People don't have the money to afford full Cisco kits. So they will choose the open standard, OSPF. And Cisco realized that, and they pulled out EIGRP from the syllabus in this version. So they strip it out and they leave OSPF there. If you go to the CCNP route, I expect you'll see EIGRP in there, because it is still used in some networks. But yeah, OSPF is the open standard, so it was adopted more. Right. So here, right. So the next hop. So exit interface and next hop. So the interface here will be the interface that the router is using to forward traffic. So the interface that it is forwarding traffic to. And then in some of them, you'll see an IP next hop. Yeah. So IP next hop there. Here too. So the gateway of last resort is that. So this is the next hop IP. And this network 0000 is a very special network. So always there's just something to memorize. You can see it a little more clearly here. In this, ignore the letters there, but that network there, 0.0.0.0/0, that is, it is a wildcard. So we asked about wildcards before. So this is like the largest wildcard you could ever see. This is like, if you do any Linux, you'll know the asterisks. This is like the largest wildcard, which means all networks. So basically what the gateway of last resort or the default route says is if you go through this whole table and you don't match any of those routes there, come to me, match me, because everything will match on this. And in this specific case, with this default route, this router is saying, if you don't match anything here, come to this route, match, and send to this guy, 10042. So here, 10042, you've seen it up here as well. And you'll see in realistic networks, this will be your gateway out to the internet. So if you have, if you have 50 routers in your network, and you have a routing table with 700,000 routes, and that is a realistic number now. If you have traffic going out to the internet, you will still have a lot of those, a lot of packets matching this rule. And all of these will be going out to the internet. And the other packets that match here will likely be internal traffic. So basically, when an engineer reads a table, they will see, okay, these are all internal routes, and these all go to offices and cabinets and buildings that we own and stuff. And then traffic out to the internet matches this default route because we don't have a more specific route to the internet. Now, we also discussed how routers use the information in their routing tables to forward these packets by default using the destination address in every packet. So of course, routers look at the destination address and they use this information in this table to determine where to forward packets to based on that destination address. So if they know it going to X, Y, Z, A, they will look at their table and use the lookup. Well, they will perform a lookup in that table to determine where is the next best hop to send a packet to try to get it to its destination. So it always looks at its destination address, not the source address. We also discussed the concepts of longest match lookup, administrative distances, and routing protocol metrics, or just metrics, to show how routers having multiple matching routes for a destination address and multiple valid sources of a particular route and multiple valid paths to a particular route respectively. So that's how the routers handle these different concepts. So we went through all of this stuff. Longest match lookup is saying if you go into a host and the table has a route to that specific host, so like a /32 matching one IP address, the router will prefer that over something matching like a /8 because that subnet mask is so specific and it matches only one host. So the router will match both of those routes, but it will match the more specific one better. So it will send traffic there. Administrative distances tells the router how trustworthy a particular source of information is. So lower ADs or lower administrative distances are always better. And we had a table listing out the default ADs for protocols. And I said that is a very important thing to memorize as much as you could, especially for the exam, just try and memorize it. But you need to understand as well, lower is always better. So we'll go through static routes today. Static routes have a default AD of 1, which means it's pretty trustworthy, right? Because we put it into the router ourselves. But something like BGP usually is not so much trustworthy because we usually get BGP routes from the internet. So you'll see it has a pretty high AD. So we could usually override it inside our network easily. And then the metrics determine how good or how bad different parts within the same protocol are. So if you have a slow link and then another faster link going to the same network, OSPF might say, okay, I see this link has much more bandwidth than this other link. Let me assign this a lower metric so that traffic will prefer to flow here over the slower link, but still keep that slower link with that higher metric in case a link fails. Traffic will always fail over to this slower link. And yeah, that's it. Right, so now let's move on to configuring IPv4 and IPv6 static routing. Now that we understand how routers forward packets using their routing tables, let's examine some methods of getting routes into these routing tables. Routers will always learn about their directly connected networks as soon as we enter IP address information on their interfaces. These networks will usually have two codes to the left, an L for local, for the specific /32 network that we have configured directly on the interface, and a C, or connected, for the entire network that the interfaces are part of. Remember that these routes have an AD of 0, an administrative distance, so that they will always be the most preferred and will thus be installed in the routing table. So that's what we're talking about, right? These here. Oh, L's, sorry, L's. So you have C's and L's. So this, from this routing table, we could just look at the C and the L here, and we could tell that somebody entered an IP address of 172.17.0.1 on the interface, and the subnet mask was /24 or 255.255.255.0. So you see the specific /32, that is one single IP address. And because it's L, it means it's local to this router, which means somebody put that exact IP address into this router. But this wasn't only one IP address, right? Because of the subnet mask, this was part of a bigger network. So that's where the C comes in. The C means we are directly connected to this whole network. We have an IP address in the network, which is this, but we are directly connected to this network. And that network is 172.17.0.0/24. So the C means we have a direct connection to this network. The L means we have that direct connection through this IP address that we have configured on here. And I could go through the C's and the L's as well to see different networks that we have here. So if you boot up a brand new router and you configure two IP addresses on two interfaces in two different networks, you'll likely see four of these, right? So you'll see two L's for the two IP addresses that we configured, and then two C's for the two networks that we have directly connected to us. So that's what the C's and the L's mean. However, we can't directly connect all of our networks to a single router, because of course, we can't have fibers coming back all the way to one single router in one data center. It doesn't make sense. We need to distribute our routers. So the simplest way to tell a router about the networks reachable via remote routers or via other routers is via the configuration of static routes on that router. A static route is simply a route that you manually configure on a router. During this configuration, you enter all of the information to create a row in the routing table. You configure the following: network, prefix, next hop, and then optionally the AD, or the administrative distance. So these are the ways you could configure it. So there are two ways we can configure our static routes: IP space route space destination network subnet mask IP address of next hop neighbor, and then the AD and literally the word permanent. These are two optional fields. So you'll see this here, two optional fields as well. And the only difference between this method and this method is in one, we do IP route, destination network, subnet mask, IP address of next hop, IP route, destination network, subnet mask, interface to exit. So in some special cases, we could configure our next hop as an interface instead of an IP address. So just as an example here, we have two routers here, we have a link, and we want to set up static routes between these two routers. So just go in your router, go in config mode, type in IP route 172.16.1.0 space 255.255.255.0 space and the next hop IP 172.16.2.1, which is the IP on this side. So we go in here, so this will be router A here, A, and we go here and we put in this exact command, which tells this router if you want to reach 172.16.1.0/24, which is 255.255.255.0, then go to 172.16.2.1, which is this guy. So you can see before we put in this route, router A knew how to reach 172.16.2.1 because this is a directly connected link. So it got those L's and those C's installed because we put in an IP address here before, right? So what we're doing now is we tell in router A, hey, you don't have a direct connection to this network, but I want to tell you how to reach this network. So if you want to reach this network, which is this network on the side, then IP route 172.16.1.0, 255.255.255.0, then go to 172.16.2.1. So send your traffic for this network to this guy, and he will figure out how to get it to here. And in this case, you see, he has a directly connected network here. So he will obviously know how to get the traffic to there. Now, the other special case is in point-to-point links. So the most popular point-to-point link is a serial link. So we don't really see serial links too much anymore, but Cisco likes them a lot. So if you still have a router with a serial link, you could theoretically put IP route 172.16.1.0, 255.255.255.0, and then the next hop interface, so S000. The problem I have with this is it's only for serial links, and really in my experience, I've never seen interfaces being used here. If you use this mode on a non-point-to-point interface or a non-serial interface, then like an Ethernet interface, you'll end up getting a lot of problems with the router, because what kind of happens in a nutshell is every time the router tries to send traffic to this interface, it kind of tries to resolve it to an IP with every single packet, and it slows down the router a lot. So Cisco says try to use next hop IPs as much as possible. So as we mentioned before, we should only use a next hop interface if we are dealing with point-to-point links or P2P links. Most of the time, next hop IPs are preferred. The options in square brackets are optional. If the administrative distance is not specified, static routes assume a default AD of 1. So that's from the table we had last class, right? By default, static routes have an AD of 1. Also by default, if the permanent keyword is not included, the static route is removed if the next hop address or exit interface becomes unavailable. So remember I said here, we were telling router A, hey, if you want to reach this network, go to this guy. But what happens if router A doesn't know how to reach this guy, right? It doesn't make sense. He'll be trying to send this traffic to an address that he doesn't know how to reach, so he doesn't know where to forward these packets to. So if we put this exact command and router A doesn't know how to reach this guy, this 172.16.2.1 here, so just as an example, if router B loses power, or if this link breaks or something, with this exact command, router A is going to remove this route from the table. So if you do a show IP route, you'll see that this entry doesn't show up if this next hop isn't reachable. If we want to override that, and we want to say always keep this route, no matter what, leave this in the routing table, then you just add the word permanent after here. So you put space permanent. So if we want to ensure that the route remains in the table no matter what, we include the permanent keyword. Now, static routes offer us an incredible amount of control and flexibility on our networks. They can be used to allow us to direct traffic in any special way that we require. Several special configurations for static routes exist. We will examine some of them now. Static default routes are special static routes with the destination network and subnet mask both specified as all zeros. They are used to provide a gateway of last resort. So we discussed that in the table just now, right? So one way of getting that gateway of last resort, or that default gateway, is by specifying it statically. So you have a few ways you can get it into that table, into the routing table. One way is by putting a static route and just specifying what the next hop should be if it doesn't match any other entry in the table. So this means that the route is used when the destination address of a packet matches no other entry in the routing table. Without a default route in the table, traffic not matching any specified routes is dropped. So remember, I spoke about this last class or class before, right? It's an important thing to memorize. If you do have a default route in your table, or a gateway of last resort, as it's sometimes called, if you don't have it, your traffic will be dropped and a special ICMP message is sent back to whoever was trying to send the traffic, which says destination unreachable. As a common CCNA question. Static default routes are thus very important. So this is the command again. So we start off with IP space route as we did before, but in this case, instead of specifying just one network, we did 0.0.0.0 space 0.0.0.0, which says any network in the table, anybody can match this. And then of course we specify the next hop 10.0.3.1. So we say, well, we literally type this in, and this is what shows up. So S 0.0.0.0/0. We see our default AD there of 1, and then the via and this guy. It shows up here as well in better words. Gateway of last resort is this guy. The network 0.0.0.0. Is this part kind of redundant? But this is the important part. So gateway of last resort is this guy. So if you go through and you don't match any other routes here, then send it to this guy, and he will hopefully know how to deal with it. Yeah, so this is our static default gateway. Even though we have been largely using IPv4 to demonstrate our concepts, most of these concepts can be extended to IPv6 addresses fairly easily. So to configure a static default route in IPv6, we use the following syntax. IPv6 space route. So instead of IP route, we're doing IPv6 route, and then network / prefix, and then next up IP or exit interface, and then AD or permanent, just as we had before. These two things, you don't need to put them in, but if you want to change the AD, or if you want to make it permanent, just put in the actual number for your AD here, or the permanent keyword. So this syntax is very similar to the IPv4 version of the command, except that we use the network / prefix notation instead of the network subnet mask notation. So IPv6 space route space whatever network it is / and the subnet mask. So instead of putting just the network here and then space whatever FFFFFF or 00 in the other notation, we could just put a slash notation, which is much easier in IPv6 as you could imagine. And then the next hop. So IPv6 space route space network / prefix space next hop IP. And in a lot of other vendors, you can do this for IPv4 as well. So you would have put, just as an example, IP route and then 192.168.1.0 / 24 in other vendor equipment. In Cisco, you can't do that. You have to do the dotted decimal notation, which is harder to write, but that's Cisco will. So you can do this for any network there, even with a 128 there. So default static route, right? So this example just shows the default static route for an IPv6 address. So IPv6 space route space ::/ 0, and then space and the interface or the IP address, just like with IP route. The difference is that we use this special notation instead of the 0.0.0.0. We use ::/ 0. So just memorize this. This is the same number that will be used for all IPv6 default routes. And then the next up interface or the next up IP. So note that the IPv6 static default route is configured with the command IPv6 space route space : 0 ::/ 0, and then the next up IP or exit interface. And then AD there if we want to change it. Also note that the IPv6 address family has its own routing table. So I don't think I made the points for this last class, but IPv4 and IPv6, when you're running IPv6 in a network, IPv6 has its own routing table. So you won't see like an IPv4 route in one row and an IPv6 route in the next row. They are two separate tables entirely. So to view the IPv6 routing table, you use the command show IPv6 route as opposed to show IP route for IPv4. So show IPv6 route, and this is what you'll see. So it looks very similar to the IPv4 one, right? So you see it named IPv6 routing table and 6 entries. So you know what you're watching. Same codes, yeah, OSPF, connected, local, static, RIP, PGP, all those things we're familiar with. Same, well, the exact same letters here actually. The difference here will be the networks. These will be IPv6 networks as opposed to IPv4. And you can see, right, so we have one static route here, and we have that AD of 1 and that metric of 0, just as we are accustomed to. I'm not seeing any next hop IPs here. Oh, look here, right, look, next hop IP there. So see the static route here, via, and this guy. So the next hop IP here, and the interface we're using to forward out the traffic, just as we did in IPv4 routing. So you see it very similar, it's just the networks and the prefixes that are different here. So for both IPv4 and v6, static routes can be called different names depending on whether the destination network is a single IP or host or an entire subnet or network. So I'm just making this point because Cisco kind of split them up in static routing. So if a static route points to a single host, it is known as a host route. So when you hear the term host route, just think a static route or a route to one host, one machine, or one server, or whatever it is. So host routes are configured with the subnet mask set to all ones, 255.255.255.255. And that ensures that the route matches only that single IP. Since these routes are the best, most specific match to that host, all traffic to that host will follow the static route. So you can see that here, right, S. So you see the S for static, which means that we configure a static route here, And you see this is the network and this is the subnet mask here. So very, very particular with this subnet, with this subnet mask here, you see the /32, which means that we put all of those 255s, and this will not match anything else in this network. So just as an example, if there was a network 192.168.1.0/24, this wouldn't match that because it's only a /32. So whatever host has 192.168.1.1/32 configured in it, this route will match that, and it will send the traffic to this next hop only for that one single host. On the other hand, static routes to entire network ranges are called the network routes. So it makes sense, right? These are the routes that we have been seeing in our examples so far. They direct traffic for entire remote networks. Since they are less specific, traffic that does not match any specific smaller routes will be forwarded using these routes. So we accustomed to this. So this is here. They configured a static route to the /32 here, and they also configured a network route to this 192.168.1.0/24. This is /24 here. So this one would be the network route. This one would be the host route. So in some cases, you may want to direct traffic for a particular host through an X-link and leave traffic to everything else on the network to the same link. Just as an example of this, let me say you have a network like this, a /24 network, but you have one host on the network that is consuming like 90% of the traffic. Just as an example, if you're doing video streaming, you might have one video server that's using 90% of the bandwidth. You might have two links to that network, and you might want to say, okay, I want this one video streaming server to use link 1, and I want everything else to use link 2, so that I could kind of load balance it using this static route. So it's just one way to load balance, and it might be effective if you have one host that needs to be treated specially for any reason. Just in this case, the video server might be using way more bandwidth than everything else on the network. So notice that all of our static routes so far have been using an AD of 1, as this is the default on Cisco routers. So we know that from the table in the last presentation. However, what if we want to change this behavior? An AD of 1 is fairly low, meaning that static routes will override most other sources of information. So lower ADs, always better. So when our AD of 1 is pretty low, right? We don't have decimals here. So the only thing that could beat our AD of 1 is 0, which is directly connected. And we obviously can't directly connect much more to our routers when we run out of ports. So what if we want to change this AD of 1? However, sometimes we only want a static route to become effective if other sources of routing information fails. We can achieve this design using a concept known as floating static routes. Basically, we set a static route with a higher AD than default, so that the router only installs the route if another or better source or route fails or disappears. So you can kind of see it here. Basically, what we're doing here is we're using the same command, IP space route, and then 0000, and then an XUP IP, and then space, and we pass a number. So you see in this case, in the top one, we didn't pass a number, which means it would have been 1 by default. And in the next one, we put a number, which means it's something higher. So you can see it again here. So these are two identical static routes. So you see the network here is 192.168.2.0, and then the same one here, 192.168.2.0, same subnet mask. So it points to the same network, but we put two different NextHop IPs. So we send in the traffic through a primary link, and then we have a secondary link as well. So we're saying, okay, you can reach this network through this guy. So send it to this guy, but you can also reach the same network through this other guy. So we say through this link or through this link. So you put in two static routes for the same network. However, in one of them, we put a space and we put this number here, so 20. So when you see you have nothing here after the next up IP, just kind of assume that you see now 1 there in your head, because that's the default AD. So this one has an AD of 1, this one has an AD of 20. So the only time this route is ever going to be installed in the table is if this guy disappears. Yeah, so we have this route just primed and waiting, and it is a valid next up here, but it is a secondary or backup link. So maybe it's slower, maybe it's more expensive, maybe it's less reliable, maybe you have more loss or more latency or something across this link. So we give it a higher AD, and we say, okay, look, by default, I want you to use this guy with the lower AD, which is 1. But if you ever disappear, I want you to just take off this route, because this next hop will become unreachable, and then install this guy, because he will be your secondary option. Now, as a last note, remember that all the concepts of IPv4 static routes can apply to IPv6 as well. We can configure floating static routes in the same way on IPv6. So you see IPv6 route, : 0, next hop IP, 10. And then IPv6 route, : 0, next hop IP, 20. And then we could do one without the AD. And then you could use your knowledge of lower AD wins to figure out that this guy would be installed here, because he has nothing here. So it'll be 1 by default. He has the lowest AD, he'll be installed. If he ever fails, this guy with the 10 will be installed after that. If he fails as well, guy with the 20 will be installed. Yeah? So that's what a floating static route is. It's a static route, it's there, but it's floating. It's not really, it's not stuck in the table. It's just kind of there. And it will only be installed if the better route fails, which means if this next hop IP is not reachable anymore. If a link fails and this guy is not reachable anymore, if this router loses power, if something else happens, if the cable gets unplugged or anything, then the floating static route will just kind of slide in and get installed in the table, and then we could maintain reachability to this network. In this case, it's the default route, so we could maintain reachability out to the internet. Also remember that static routes are sometimes needed on multiple routers. For example, if we tell our router R1 how to reach a remote network on another router R2, we may also need to tell R2 how to reach the networks available on R1. So basically, R1 here only knows about these two networks that it has directly connected to it. So if we go into R1 and put a static route saying, hey, you can reach this network here using R2. So, IP route, or blah, 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 next hop this, go here. That is great for getting the information here. And then R1 will know, hey, if I want to get this information here, I send it here. And then it goes here, and it goes there. What happens when the traffic needs to come back here? R2 will see a packet destined for this guy, but he won't know what to do with it, right? He'll see information go into, right, look here, the IP address here, 10.0.0.10. He will come in here and he'll say, hey, I have a network 10.0.0.10. I have a 20 and I have a 30. And I don't know what to do with it. So he's just going to drop it. So configuring the static route on R1 isn't enough. You also need to go on R2 and configure a static route back to R1 to tell R2, if you see any traffic going to 10, send it back this side. So that's just an important point, for life. When you're configuring static routes, you usually need to configure it on 2 routers at least. You might have more depending on if you have a big router chain, but at the very least is usually 2 routers. So the router that's sending the traffic to somewhere and the router that's bringing the traffic back from somewhere. Usually you need to configure it on both places. So when you hear somebody mention a matching static route, usually this concept is what they're talking about, getting the traffic back to your source. Now that you understand how to configure static routes, let's move on to some dynamic routing. Remember, the entire point of static routes was to teach a router how to reach a remote network. So that's what I explained here, right? The whole point of putting in the static route was to tell R1 how to reach this network here that it can't see directly. Router 1 could see this network because it has a link in this network. It could see this network because it has a link in this network, but it can't see this network because it has no links directly connected here. So we put a static route to tell router 1, if you want to get something to here, send it to router 2. So that was to teach the router how to reach a remote network. We went in and we manually told this router how to get to that remote network. However, static routes do not scale well. Imagine trying to enter static routes for the entire internet. The IPv4 table was just under 800,000 routes as of 2019. So there are places you could see how many routes there are on the internet right now. When last I checked it, it was just under 800,000. So imagine trying to go into a router and saying, if you want to reach Comcast, go to here. If you want to reach Verizon, go to here. If you want to reach Sprint, go to here. It's not going to work, right? That's going to take way too much time. So due to this, as well as a number of other weaknesses, enterprises typically employ some sort of dynamic routing protocol in their networks. So what usually happens is that people deploy multiple dynamic routing protocols in their network. BGP is the one that's used on the internet, and the one used inside is OSPF. They could also use RIP or EIGRP or a few other ones. but the one in the CCNA syllabus is OSPF. And in my experience, OSPF is the most popular one used inside networks. So today we will explore one such protocol, OSPF. So OSPF, or Open Shortest Path First, so that's what OSPF stands for, is one of the most common interior dynamic routing protocols present in the modern networking world. Chances are high that you'll end up working in an environment running OSPF. There are two versions implemented in modern networks, version 2 and version 3. Version 2 is commonly implemented for IPv4 networks, while version 3 is commonly implemented for IPv6 networks, although version 3 can be used for both. So people usually do version 2 and version 3 next to each other. You could run both at the same time. And they use version 2 for IPv4 and version 3 for IPv6. For the new CCNA syllabus, Cisco has specifically asked us to focus on only OSPFv2. They have also asked us to focus only on single area OSPF. We'll talk more about areas as we get into this topic. So just a quick note, I'm not sure if Cisco wanted us to go and cover this specifically because they didn't mention it, but when I say interior dynamic routing protocols, so it is a few concepts here to understand there, right? So dynamic routing protocols, contrast that to static routing. So in static routing, you tell every single router how to reach every other router, basically. So that's dynamic versus static. So I hope you understand that. Then you have interior versus exterior. So interior versus exterior talks about a number called an AS, or an autonomous system. So think about Digicel. Digicel has their own network, right? They manage their own network from Miami all the way down to Trinidad, well, to Guyana now. So they have a big chain of routers going all the way up the islands and fibers connecting those routers. And that whole thing could be one autonomous system or one big networking system under the control of one entity, which is Digicel. So interior routing protocols are used within an AS. Exterior routing protocols, which is the opposite of interior, they are used between ASs. So let me say on both sides, Digicel wants to pair with let me say Sprint. So Sprint is fairly common. You need to use what is called an exterior routing protocol to communicate your routes between Sprint and your network. So let me say Digicel has 50 networks in their AS or in their in the whole domain of their network. They want to exchange these routes to Sprint to say that people on Sprint could reach our networks and we could reach networks in Sprint. They will use an exterior dynamic routing protocol to exchange these routes with Sprint. And that exterior routing protocol is BGP. There was one other one a while ago, but BGP is by and large the most commonly used protocol for that. So that's interior versus exterior. So usually the two protocols you'll hear most about are BGP, which is an exterior dynamic routing protocol, and OSPF, which is an interior dynamic routing protocol. So that's just a quick overview of that. Cisco didn't have it in the syllabus, but just in case anybody was wondering why I put interior here specifically. Now, OSPF belongs to a class of protocols called link state routing protocols. This means that every router running OSPF has a complete map of the network. This map is called the OSPF database, or the link state database, or LSDB. So R1, could imagine that R1 is just thinking about this nice network that is connected to, and it knows it has a link here, and then R2 has two links here, and R3 has two links here, there and there, and R5 has two links there, and R4 has two links here. So you see all of these routers, they imagine the same network because they have complete visibility of the entire network. Not all protocols are like that. Like with EIGRP, it is not a link state routing protocol. So it does not have a complete map of the network. So yeah, let's keep contrasting it just so that you understand the significance. But that is what being a link state routing protocol is. It means that you have a map, a complete map of the network. And that map is called the database, or the LSDB, which is a link state database. In order for the OSPF routers to form this map of the network, they must communicate with each other and exchange information in some way. So that makes sense, right? R1 by itself can't magically have this complete map of the network. They need to form this map somehow. And how they do that is they talk to each other. So every router will talk to its directly adjacent router here, and they will just keep exchanging messages. R1 will say, hey, you next to me. Hey, hello, what's the scene? R2 will say, hey, look, I have a R1 talking to me here. Oh, but I also have a R4 talking to me here. I also have a R3 talking to me here. Therefore, I know I'm connected to R1, R4, R3. And then R2 could spread the message. He could talk to R4, and he could send back a reply saying, hey, hello, R4, I seen you. But hey, no, I also see R1 here. I have a connection to R1. And then R4 will say, hey, okay, cool. Let me spread that to R5. Hey, R5, I connected to you, but I also connected to R2. And R2 tell me he connected to R1. And then it'll keep going like that. So through this building of information, they will eventually have a complete map of the network. And more importantly, more than having the complete topology of the network and all the routers will also exchange their networks. So if R1 had 3 links here that connected to PCs or whatever in 3 different networks, R1 would tell R2, hey, I have connections to these 3 networks here. And then that information will spread. So that R5 could send that information and get it to this way, to R1, and R1 could get it to the network here. So that's what OSPF is about. It's about building this map and making sure that R5 knows about the networks connected to R1 and the networks connected to R2 and everything else here, so that we don't need to go in and manually enter these routes anymore. These routers will talk amongst themselves, and they will exchange all of this nice information, and they will build their routing table by themselves. Yeah, so it's sounding much easier, right? So OSPF uses IP directly for this communication. It doesn't use TCP or UDP at the transport layer. It just uses IP. It uses both unicast and multicast for communications. So we mentioned unicast and multicast before. Unicast is just one-to-one communications, and multicast is one-to-many. So like a video receiver. You have one server serving traffic and many people receiving that traffic. So 224.0.0.5 is the reserved multicast address for all OSPF routers in a network, while 224.0.0.6 is the reserved multicast address for all designated OSPF routers on a network. And we'll get into what a designated router is, I believe, in the next class. Now, OSPF revolves around neighbor adjacency formation between adjacent routers. To form these adjacencies and become OSPF neighbors, routers periodically send OSPF hello messages to this special address, 224.0.0.5. So you should memorize these 2 addresses. So this is the all OSPF routers address, 224.0.0.5, and this is the one for all designated OSPF routers, 224.0.0.6. I think I've seen this one show up in a question before. They just had different examples, and they asked what is the all OSPF routers address, or the other way around. They'll ask you, well, they'll give you this and ask you what it's used for. So try to memorize these 2 addresses if you could. So this is what we just discussed, right? So this is router 1, this is router 2, and they're going to start this whole OSPF process by just saying hello. So it's called a OSPF hello message, and both of them are going to send it to each other. And in these hello messages, they're not just going to say hello. They're going to include a number of important parameters that we could configure in OSPF. Once an OSPF router receives a hello message from another router, it begins the process of adjacency formation. In order to form an adjacency, OSPF routers transition through a number of states. The final state is called the full state. Usually, you have some exceptions where you don't need to become full with your neighbor, but usually you want your routers to be in the full state. If a router becomes stuck in a state before the full state, then adjacencies do not form. Again, usually. So this is the process that we need to learn, right? So down means we never started any OSPF process, so we're just there. We didn't form any adjacency. Then we go into init, then two-way, then xstart or exchange start, then exchange, then loading, then full. And in NBME networks, which is non-broadcast multiple access networks, we're going to go through a special stage called attempt. So don't worry about this too much. In the next slide, I'm explaining what each of these stages mean. But for now, just appreciate that to become adjacent with a neighbor, so to build this map, every router needs to form an adjacency with every other directly connected router. So to build this full map, right? And to become adjacent or to form that relationship, they need to go through all of these stages. So they won't just go from down into full and suddenly they are neighbors. They need to go through all of these stages and negotiate certain things and exchange certain things. So you see here, establish adjacencies. So this is kind of like a handshake, and then synchronize databases. So they're going to exchange information and say, hey, I know about this route. Oh, but I know a better way to that route. Oh, well, let me update my side. And then they might say, oh, I just learned about this route, but this other one is an old message. So let me just delete this from my database. And on all of those things, those will be in the synchronized DB stages. And then full is when you finish talk and you have your database up to date. So these are the actual explanations now. Let's discuss each of these states in turn. So in the down state, the routers simply don't know about each other. So this is before they start exchanging any information. In the attempt state, this state is only present on non-broadcast multiple access or NBMA networks or NBMA links. And it's just a special type of link for certain networks like frame relay networks. So I haven't seen much of these networks anymore. Frame relays are old technology, but just appreciate that it exists. So this means that the router is trying to form a layer 2 adjacency. In the init stage, the router has received a hello packet from another neighbor, and in the two-way state, both routers have received hello packets and have established bidirectional communication. So this one I know is very popular. Cisco just used to list out these 4 states, and they used to ask, what is the state where both routers have now established bidirectional communications? And of course, 2 is the answer. So it's just to memorize these things basically. But I have used these things in real life a lot. So just a real life example. Actually, I'll do the example after. So in two-way state, both routers have received hello packets and have established bidirectional communication. So they both said hello to each other, and now they know that they can talk to each other. In XStart, both routers have begun exchanging link state information. So they start, sending their database entries. And in exchange, both routers are sending each other summaries of their full database. In loading, routers have finished transmitting, but are waiting on the full database from their pair. So it means, I finished sending out all my information, but I'm still waiting on some database information from the other guy. And then in full state, both routers now have the same LSDB or the same database and are fully adjacent. So as I said, full is the final stage. Right, so some real life examples now. So usually you will see a router go through these stages. So we'll go through, I think you're going through the examples in the lab. There's a command you can run, and you'll see the state between this router and the pair routers. And you'll see it as down or attempt or init or two-way or xstart or all these things. Now, usually you will see a router go through this, and depending on how big your database is or how big your network is, it might take, let me say, up to 5 minutes to go into full state. Usually it's much smaller in these small networks that we have. It might take 5 seconds or 10 seconds. But sometimes you might see it stuck in the two-way state, or stuck in the xstart state, or stuck in the exchange state. And in those cases, you might wait for half an hour and it'll still be stuck in the xstart state or stuck in the exchange state. And you need to be able to troubleshoot this. So you'll come back to this same slide or a Cisco white paper, and you'll say, okay, xstart. So both routers have begun exchanging link state information. Okay, so I know they're sending hello packets. I know they're establishing bidirectional communications, but somehow they're being stuck here. And you could use this definition to help you troubleshoot. So things like MTU problems, different network types. So I tell you, NBMA is one network type. If you configure a different network type on the next side, the routers will be stuck in this way. If you have a lot of packet loss, these hello packets or these LSDB summaries might be lost somewhere along the network. If the router overloaded, it might not be able to process these hello messages or process these exchange messages. You have a bunch of different things that could come up. But this is the baseline for it, just knowing what these different words mean in the whole OSPF process. Now, in most cases, routers will transition to the full state, letting us know that the OSPF adjacency was successful. However, exceptions exist. So when I believe in a few slides in the next class, we'll go through one special case where you expect that the router will stay in the two-way state. When we talk about designated routers, you'll see that some of them we expect them to stay in the two-way state. But most of the time, we expect them to go in the full state. Now, every OSPF router is identified with a 32-bit unique numeric identifier called its router ID. By default, OSPF first looks at the highest IP address configured on its loopback interface to be its router ID. So if you configure 3 addresses on the router ID, OSPF will go and try to find the highest of those addresses and configure that to be its router ID. If no IP addresses are configured on the loopback interfaces, it looks for the highest IP address on the physical interface. Just as a best practice, we should always configure a unique IP address on a loopback interface in every OSPF router and manually set our router ID to this address. So I believe in the lab you should have seen the command router ID and you put in the actual router ID. So that's a best practice. I have seen people do public IP addresses on the loopback for this. So just to make sure the router ID is unique, they will take one public IP and they will put it on that router. Just so that they know that public IP is not going to be used anywhere else. And we can therefore set our router ID to be that public IP and be very safe with that. Because if you have a router ID used in 2 different routers, you'll see a bunch of problems with the database, with the LSDB. So usually you want to make sure your router ID is unique, and you want to set it manually just to make sure it is what you think it should be. But also memorize this process. So OSPF first looks at the highest IP on the loopback interface, and then it looks at the highest IP on the physical interface. But it looks at the loopback interface first. So that's a common Cisco question too. And they'll have highest IP on loopback, lowest IP on loopback, highest IP on physical, and they'll ask what is the first address that OSPF will pick. Yeah, and that's it. So I know OSPF is a very heavy topic, so I try to split it down the middle and break it in this class, and in the next class we'll finish it off and you'll get into some of those other smaller topics. So for now, I think you have done the lab already. Feel free to do it over with your fresh OSPF knowledge. Our next class we'll finish OSPF and we'll go into full stop redundancy protocols and we'll start section 4. For today, it's supposed to be up to lab 14. Yeah. So lab 14 here, configuring NAT. So yeah, next class we're going to go into NAT. But for today, take a try on lab 14 and let me know if you have any issues, as normal. Okay, any questions?